Flash memory is an electronic non-volatile computer storage medium that can be electrically erased and reprogrammed. Introduced by Toshiba in 1984, flash memory was developed from EEPROM. There are two main types of flash memory, which are named after the NAND and NOR logic gates. The individual flash memory cells exhibit internal characteristics similar to those of the corresponding gates, whereas EEPROMs had to be completely erased before being rewritten. NAND-type flash memory may be written and read in blocks which are generally much smaller than the entire device. NOR-type flash allows a single machine word to be written to an erased location, or read independently. The NAND type is primarily used in memory cards, USB flash drives, solid-state drives, and similar products. For general storage and transfer of data, NAND or NOR flash memory is also often used to store configuration data in numerous digital products, a task previously made possible by EEPROM or battery-powered static RAM. One key disadvantage of flash memory is that it can endure a relatively small number of write cycles in a specific block. Example applications of both types of flash memory include personal computers, PDAs, digital audio players, digital cameras, mobile phones, synthesizers, video games, scientific instrumentation, industrial robotics, medical electronics, and so on. In addition to being non-volatile, flash memory offers fast read access times, as fast as dynamic RAM, although not as fast as static RAM or ROM. Its mechanical shock resistance helps explain its popularity over hard disks in portable devices, as does its high durability, being able to withstand high pressure, temperature, immersion in water, etc. Although flash memory is technically a type of EEPROM, the term EEPROM is generally used to refer specifically to non-flash EEPROM, which is erasable in small blocks, typically bytes. Because erase cycles are slow, the large block sizes used in flash memory erasing give it a significant speed advantage over non-flash EEPROM when writing large amounts of data. As of 2013 update, flash memory costs much less than byte programmable EEPROM and has become the dominant memory type wherever a system requires a significant amount of non-volatile, solid-state storage. History. Flash memory was invented by Dr. Fujio Matsuoka while working for Toshiba circa 1980. According to Toshiba, the name Flash was suggested by Matsuoka's colleague, Shoji Ariazumi, because the erasure process of the memory contents reminded him of the flash of a camera. Matsuoka and colleagues presented the invention at the IEEE 1984 International Electron Devices meeting held in San Francisco. Intel Corporation saw the massive potential of the invention and introduced the first commercial NOR-type flash chip in 1988. NOR-based flash has long erase and write times, but provides full address and data buses, allowing random access to any memory location. This makes it a suitable replacement for older read-only memory chips, which are used to store program code that rarely needs to be updated, such as a computer's BIOS or the firmware of set-top boxes. Its endurance may be from as little as 100 erase cycles for an on-chip flash memory, to a more typical 10,000 or 100,000 erase cycles, up to 1 million erase cycles. NOR-based flash was the basis of early flash-based removable media. Compact flash was originally based on it, though later cards moved to less expensive NAND flash. NAND flash has reduced erase and write times, and requires less chip area per cell, thus allowing greater storage density and lower cost per bit than NOR flash. It also has up to 10 times the endurance of NOR flash. However, the I/O interface of NAND flash does not provide a random access external address bus. Rather, data must be read on a block-wise basis, with typical block sizes of hundreds to thousands of bits. This makes NAND flash unsuitable as a drop-in replacement for program ROM. Since most microprocessors and microcontrollers require byte-level random access, in this regard, NAND Flash is similar to other secondary data storage devices, such as hard disks and optical media, and is thus very suitable for use in mass storage devices, such as memory cards. The first NAND-based removable media format was Smart Media in 1995, and many others have followed, including Multimedia Card, Secure Digital, Memory Stick, and XD Picture Card. A new generation of memory card formats, including RSMMC, mini-SD and microSD, and Intelligent Stick, feature extremely small form factors. For example, the microSD card has an area of just over 1.5 square centimeters, with a thickness of less than 1 millimeter. MicroSD capacities range from 64 megabytes to 200 gigabytes, as of March 2015. Principles of operation. Flash memory stores information in an array of memory cells made from floating-gate transistors. In traditional single-level cell devices, each cell stores only one bit of information. Some newer flash memory, known as multi-level cell devices, including triple-level cell devices, can store more than one bit per cell by choosing between multiple levels of electrical charge to apply to the floating gates of its cells. The floating gate may be conductive or non-conductive. Floating gate transistor in flash memory. Each memory cell resembles a standard MOSFET, except that the transistor has two gates instead of one. On top is the control gate, as in other MOS transistors, but below this there is a floating gate insulated all around by an oxide layer. The FG is interposed between the CG and the MOSFET channel. Because the FG is electrically isolated by its insulating layer, electrons placed on it are trapped until they are removed by another application of electric field. Counterintuitively, placing electrons on the FG sets the transistor to the logical 0 state. Once the FG is charged, the electrons in it screen the electric field from the CG, thus increasing the threshold voltage of the cell. This means that now a higher voltage must be applied to the CG to make the channel conductive. In order to read a value from the transistor, an intermediate voltage between the threshold voltages is applied to the CG. If the channel conducts at this intermediate voltage, the FG must be uncharged, and hence, a logical 1 is stored in the gate. If the channel does not conduct at the intermediate voltage, it indicates that the FG is charged, and hence, a logical 0 is stored in the gate. The presence of a logical 0 or 1 is sensed by determining whether there is current flowing through the transistor when the intermediate voltage is asserted on the CG. In a multi-level cell device, which stores more than one bit per cell, the amount of current flow is sensed. In order to determine more precisely the level of charge on the FG, internal charge pumps, despite the need for high programming and erasing voltages, virtually all flash chips today require only a single supply voltage, and produce the high voltages using on-chip charge pumps. Over half the energy used by a 1.8V NAND flash chip is lost in the charge pump itself. Since boost converters are inherently more efficient than charge pumps, researchers developing low-power SSDs have proposed returning to the dual VCC, VPP supply voltages used on all the early flash chips, driving the high VPP voltage for all flash chips in a SSD with a single shared external boost converter. In spacecraft and other high-radiation environments, the on-chip charge pump is the first part of the flash chip to fail. Although flash memories will continue to work, in read-only mode, at much higher radiation levels, NOR flash in NOR flash, each cell has one end connected directly to ground, and the other end connected directly to a bit line. This arrangement is called NOR flash because it acts like a NOR gate. When one of the word lines is brought high, the corresponding storage transistor acts to pull the output bit line low. NOR flash continues to be the technology of choice for embedded applications requiring a discrete non-volatile memory device. The low read latencies characteristic of NOR devices allow for both direct code execution and data storage in a single memory product. Programming a single-level NOR flash cell in its default state is logically equivalent to a binary 1 value, because current will flow through the channel under application of an appropriate voltage to the control gate, so that the bit line voltage is pulled down. A NOR flash cell can be programmed, or set to a binary 0 value, by the following procedure. An elevated on voltage is applied to the CG. The channel is now turned on, so electrons can flow from the source to the drain. The source drain current is sufficiently high to cause some high-energy electrons to jump through the insulating layer onto the FG, via a process called hot electron injection. Erasing to erase a NOR flash cell, a large voltage of the opposite polarity is applied between the CG and source terminal, pulling the electrons off the FG through quantum tunneling. Modern NOR flash memory chips are divided into erase segments. The erase operation can be performed only on a blockwise basis. All the cells in an erase segment must be erased together. Programming of NOR cells, however, generally can be performed one byte or word at a time. Nand Flash also uses floating gate transistors, but they are connected in a way that resembles a NAND gate. Several transistors are connected in series, and the bit line is pulled low only if all word lines are pulled high. These groups are then connected via some additional transistors to a NOR-style bit line array in the same way that single transistors are linked in NOR flash. Compared to NOR flash, replacing single transistors with serial-linked groups adds an extra level of addressing. Whereas NOR flash might address memory by page then word, NAND flash might address it by page, word and bit. Bit-level addressing suits bit serial applications, which access only one bit at a time. Execute-in-place applications, on the other hand, require every bit in a word to be accessed simultaneously. This requires word-level addressing. In any case, both bit and word addressing modes are possible with either NOR or NAND flash. To read data, first the desired group is selected. Next, most of the word lines are pulled up above the VT of a programmed bit, while one of them is pulled up to just over the VT of an erase bit. The series group will conduct if the selected bit has not been programmed. Despite the additional transistors, the reduction in ground wires and bit lines allows a denser layout and greater storage capacity per chip. In addition, NAND flash is typically permitted to contain a certain number of faults. Manufacturers try to maximize the amount of usable storage by shrinking the size of the transistors. Writing and erasing. NAND flash uses tunnel injection for writing and tunnel release for erasing. NAND flash memory forms the core of the removable USB storage devices known as USB flash drives, as well as most memory card formats and solid-state drives available today. Vertical NAND memory stacks memory cells vertically and uses a charge trap flash architecture. The vertical layers allow larger areal bit densities without requiring smaller individual cells. Structure of NAND uses a charge trap flash geometry that stores charge on an embedded silicon nitride film. Such a film is more robust against point defects and can be made thicker to hold larger numbers of electrons. NAND wraps a planar charge trap cell into a cylindrical form. An individual memory cell is made up of one planar polysilicon layer containing a hole filled by multiple, concentric vertical cylinders. The hole's polysilicon surface acts as the gate electrode. The outermost silicon dioxide cylinder acts as the gate dielectric, enclosing a silicon nitride cylinder that stores charge. In turn, enclosing a silicon dioxide cylinder as the tunnel dielectric that surrounds a central rod of conducting polysilicon which acts as the Conducting channel. Memory cells in different vertical layers do not interfere with each other, as the charges cannot move vertically through the silicon nitride storage medium, and the electric fields associated with the gates are closely confined within each layer. The vertical collection is electrically identical to the serial linked groups in which conventional NAND flash memory is configured. Construction growth of a group of NAND cells begins with an alternating stack of conducting polysilicon layers and insulating silicon dioxide layers. The next step is to form a cylindrical hole through these layers. In practice, a 128 GB NAND chip with 24 layers of memory cells requires about 2.9 billion such holes. Next, the hole's inner surface receives multiple coatings, first silicon dioxide, then silicon nitride, then a second layer of silicon dioxide. Finally, the hole is filled with conducting polysilicon. Performance as of 2013. NAND flash architecture allows read and write operations twice as fast as conventional NAND and can last up to 10 times as long, while consuming 50% less power. They offer comparable physical bit density using 10 nanometer lithography, but may be able to increase bit density by up to 2 orders of magnitude. Limitations. Block erasure. One limitation of flash memory is that, although it can be read or programmed a byte or a word at a time in a random access fashion, it can only be erased a block at a time. This generally sets all bits in the block to 1. Starting with a freshly erased block, any location within that block can be programmed. However, once a bit has been set to 0, only by erasing the entire block can it be changed back to 1. In other words, flash memory offers random access read and programming operations, but does not offer arbitrary random access rewrite or erase operations. A location can, however, be rewritten as long as the new values 0 bits are a superset of the overwritten values. For example, a nibble value may be erased to 1111, then written as 1110. Successive writes to that nibble can change it to 1010, then 0010, and finally 0000. Essentially, erasure sets all bits to 1, and programming can only clear bits to 0. File systems designed for flash devices can make use of this capability, for example, to represent sector metadata. Although data structures in flash memory cannot be updated in completely general ways, this allows members to be removed by marking them as invalid. This technique may need to be modified for multi-level cell devices, where one memory cell holds more than one bit. Common flash devices such as USB flash drives and memory cards provide only a block-level interface, or flash translation layer, which writes to a different cell each time to where level the device. This prevents incremental writing within a block. However, it does not help the device from being prematurely worn out by intensive write patterns. Memory wear. Another limitation is that flash memory has a finite number of program erase cycles. Most commercially available flash products are guaranteed to withstand around 100,000 PE cycles before the wear begins to deteriorate the integrity of the storage. Micron Technology and Sun Microsystems announced an SLC NAND flash memory chip rated for 1 million PE cycles on the 17th of December 2008. The guaranteed cycle count may apply only to block 0, or to all blocks. This effect is partially offset in some chip firmware or file system drivers by counting the writes and dynamically remapping blocks in order to spread write operations between sectors. This technique is called wear leveling. Another approach is to perform write verification and remapping to spare sectors in case of write failure, a technique called bad block management. For portable consumer devices, these reroute management techniques typically extend the life of the flash memory beyond the life of the device itself, and some data loss may be acceptable in these applications. For high-reliability data storage, however, it is not advisable to use flash memory that would have to go through a large number of programming cycles. This limitation is meaningless for read-only applications such as thin clients and routers, which are programmed only once or at most a few times during their lifetimes. In December 2012, Taiwanese engineers from Macronix revealed their intention to announce at the 2012 IEEE International Electron Devices meeting that it has figured out how to improve NAND flash storage read-write cycles from 10,000 to 100 million cycles using a self-healing process that uses a flash chip with onboard heaters that could anneal small groups of memory cells. The built-in thermal annealing replaces the usual erase cycle with a local high-temperature process that not erase erases the stored charge, but also repairs the electron-induced stress in the chip, giving write cycles of at least 100 million. The result is a chip that can be erased and rewritten over and over, even when it should theoretically break down. As promising as Macronix's breakthrough could be for the mobile industry, however, there are no plans for a commercial product to be released anytime in the near future. Read disturb. The method used to read NAND flash memory can cause nearby cells in the same memory block to change over time. This is known as read disturb. The threshold number of reads is generally in the hundreds to thousands of reads between intervening erase operations. If reading continually from one cell, that cell will not fail but rather one of the surrounding cells on a subsequent read. To avoid the read disturb problem, the flash controller will typically count the total number of reads to a block since the last erase. When the count exceeds a target limit, the affected block is copied over to a new block, erased, then released to the block pool. The original block is as good as new after the erase. If the flash controller does not intervene in time, however, a read disturb error will occur with possible data loss if the errors are too numerous to correct with an error correcting code. X-ray effects. Most flash ICs come in ball grid array packages, and even the ones that do not are often mounted on a PCB next to other BGA packages. After PCB assembly, boards with BGA packages are often X-rayed to see if the balls are making proper connections to the proper pad, or if the BGA needs rework. These X-rays can erase programmed bits in a flash chip. Erased bits are not affected by X-rays. Some manufacturers are now making X-ray-proof SD and USB memory devices.